All right, guys, so what we're looking at now is matrices. And pretty much that's all what this chapter is going to be. 8.1, we're only going to go 8.1 to 8.4. We're not going to talk too much about 8.5. And that's mainly going to be it. Most of this is going to be a recap of what you've done before with matrices. Now in this section, we'll study streamline techniques for solving systems of linear equations using these here. Now, when we have a matrix, it is rows by columns. And it's always read the number of rows by the number of columns. Now, for any, and then, the entry in the ith row and jth column is denoted by the double subscript aij. Now, whenever we're talking about elements, individual ones, it's always in lowercase. So if we're talking about matrix A, we'd have element aij, row, column. For instance, A23 refers to the entry in the second row and third column. A matrix that only has one row is called a row matrix, and a matrix that only has one column is called a column matrix. And a matrix having m rows and n columns is said to be of the order m by n. So most of this is recap. If m is equal to n, then it is a square matrix. Number of rows is equal to the number of columns. And the diagonal is this here kind of where the numbers line up. Questions on this so far? No? So if we want to look at the order of each one of these here, so our first one, letter A, what would be this here? This would be a 1 by, because we have one row and one.
1 by 4.
Now what would we call this? Because we have a row. 2 by 2, and this would be a square because the number of rows and the number of columns are the. And this
3 by 2.
3 by 2. And it wouldn't have a special name for it because the number of rows and columns are not the same, and we don't have a row or a column. So it's just a 3 by 2. Now, a matrix derived from a system is written in the form with the constant terms on the right in the augmented matrix of the system. Moreover, we have these coefficient system. Now, if we take a system of equations, we can write it in augmented or coefficient form. And there's a main difference between the two. An augmented matrix has the numbers in front of the x, y, and z, any of the variables, with a dotted line in what it's equal to. The coefficient matrix is just the coefficients, the numbers in front of the variables. And that's the only real difference between the two. So if we're actually solving, we're going to use an augmented matrix because we need what it's equal to. And that's the one you're used to using. Because when we were plugging them in and solving in last chapter for the system of equation, we were using an augmented matrix. Now note 0 for any missing variables. Before we end, elemental row operation. Now these we'll look at. I'm not going to make you do these here. Mainly because if you're trying to do these elemental row operations to solve, they are very tedious and very time consuming. And what they're saying is we can do several things. We can interchange two equations. We can multiply an equation by a non-zero constant. And we can add a multiple of an equation to another. Or we can subtract it. And these here are kind of the notations that we can have for it. Now what we're really wanting to do is we're wanting to use this. Let me go back. And we're wanting to take a matrix. Like this here. And what we want to get in the end and these obviously aren't the answers. If that was, that'd be a miracle. But I can just pull them out of my head like that. But what we're trying to do is we're trying to manipulate these equations to rewrite them in this here, which would be a reduced row epsilon form so that we can get the answer, or RREF. And to get that, we can manipulate the equations, adding one to another and going back and forth with this here so that we get them in this form. And that's what the whole purpose is. But getting there may not always work, because if it doesn't have a solution, it's harder to work with, and knowing where to stop. Now looking at this here, we can interchange the first and second equations of the original matrix. So we can just flip them to make it easier to work with. Because again, if we're doing a complete row, reduced row epsilon form, we want it in this diagonal of ones. Well, hey, there's a 0 here, so if I switch it, I'm a little closer to getting there. So it's using them to manipulate the equation so that we get to this diagonal of ones. Because now I have a 1 and 1, so it's a little bit closer. And then it would be working with, okay, what can I do to eliminate the first one? Well, I can do 2 times row 1 added to row 3, because negative 1 times 2 is negative 2, plus 2 gives me 0. So it's a little bit closer to getting there. And it's manipulating these equations in this fashion to trying to get there. Now, another thing we can do is we can multiply it by a non-zero constant. So if we look at this here, well, if I want to get this to be a 1, we can multiply everything by 1/2. Or we can do a combination of the two and do negative 2 times row 1 and add it to row 3, which I was kind of talking about, or kind of we can look at that. So there's different things we can do. Questions on this here? Gaussian elimination with back substitution. Now, what they're going to talk about doing and what they're going to show is using these row manipulations that we just looked at, adding them together, multiplying by these non-constant zeros, and then adding or multiplying and adding them together, using those to solve. However, back and forth. So we have this here. Now, what we would do to solve this is that we would write it in a augmented matrix. So if we look at the first one, well, it's 0 for x, 1 for y, 1 for z, 2, negative 3. Then we have 1, 2, negative 1, 2, 4. And what we want to do from this point is work it down as far as we can. Now, we're not going to go to a reduced row epsilon form. We're just going to go to a row epsilon form for this one here. And yes, that's what I would do at this point here. So I would take that graphing calculator. So it's a 4 by 5 matrix. And the first thing we can do is type this in. Have it also. Matrix. Enter. It is a 4 by 5, 0, 1, 1, negative 2, negative 3. 1, 2, 1, 0, 2. Got it. Row 3, 2, 4, 1, 2, 4, 1, negative 3. 1. All right. Nope. Yeah, I went. The next one should be 1, negative 4. From here, we would go second width. Now we're going to go second matrix. We're going to go over to math. This time we're going to use REF. We're going to use row epsilon form. We're going to go second matrix A, enter. And we get something like this here. Okay. 3, negative 2, negative 2. Okay. So we have this here. Now, there are ways that we could have manipulated this to make it look a little bit nicer and work a little bit nicer, but this is the same thing. Now, the reason I say a little bit nicer is because this is another way that it can be written, another way that it can be manipulated. And the reason they call this a work backwards, if you notice that in this kind of description, is that, well, it starts out with W equals 3. And we work back from here. Z minus 3 equals negative 2. We add 3 to it and get Z is equal to. And we can move up and plugging them back in going up. Now, what we'll see here in a minute, and the way that I like working these a little bit better, second matrix. I like REF better. Because reduced row epsilon form gives us those diagonals of 1, which tells us negative 1, 2, 1, 3. 1, 2, 1, 3. It gives us the answer straight out. We don't have to actually go back and solve them. That's what makes it a little bit nicer. Writing these here, and then going back and solving. And especially, it's kind of tricky if it is a no solution. Now, Gaussian form is doing that exact same thing, except using the row reduced epsilon form. That's the only real difference. So questions on this here? No? That's it.